So let's go ahead and get started, and we'll do our quiz at the end of today, as I mentioned. Where we left off before we kind of talked a lot about the lab on Monday was all things relating to pointers, and we got a little bit into the weeds of it, and I wanted to make sure that this kind of subtopic was covered just one more time to make sure we're all feeling pretty good about this. And this has to do with what's referred to as the equivalence of arrays and pointers. Now, ultimately, if you look at the underlying generated assembly code, what the compiler creates for you when you use an array versus a pointer, the actual underlying code is a little bit different. But conceptually, from the programmer's perspective of what functionality you wind up developing, the empty syntax using the name of an array is literally just going to be a pointer to the first element of an array. So when we talk about array pointer equivalence, and that's a term you'll see it in the Zybook, you'll see it elsewhere, that's really what that's referring to, that we have this concept that we know pretty well, that we have these array variables that correspond to a sequential set of addresses. Given the start of an array, we can figure out where the subsequent locations in that array would be in memory. And for all the things we would like to do with pointers, we can use that array syntax, the name of the array, and that is treated as a pointer to the first element in that array. And the converse, the flip side, is also true in practice, that we can have a pointer, and depending on what we have that pointer point to and how we set up that pointer, we can have our pointer point to an array in memory. Another way we see that phrase sometimes is not all pointers have to point to an array, but all arrays do have pointers that correspond to them. So given that pointer syntax that we're becoming more familiar with, we can always use the array syntax to get the ith offset, the ith element from 0 relative to that pointer's location. X of I is the same as follow a pointer from my base pointer and adding I to it. And there are some very subtle differences in terms of the resulting code that gets generated and whether one is more efficient or easier to optimize than the other. But in terms of our perspective, which we primarily just care about, does our code work or not? Does it do what we need it to do or not? They are equivalent, and you can treat those two cases as equivalent. So our pointers need not point to an array, but every array we have has a pointer. The name of the array is the first element of that array and where that gets pointed to in memory. This code example in Replit is just meant to illustrate this. It's not doing anything too terribly deep, but let's just walk through it quickly. A couple different ways we can initialize our strings, right? We're familiar already with the kind of the empty array syntax here, where if we initialize it as a constant at the time of declaration of the array, we don't have to specify the length of that array. We could have put 6 here, we could have put 6 here, we could make it larger if we wanted to as well, but if we're initializing with a constant, the compiler is able to determine how long does that array need to be, including the space for the null byte. Given that thing we've just heard and sort of started to understand of pointer array equivalence, we can also do that as we specify a char star instead of a char array and say, my char star is a name pointer. It also can point to an array, and we can provide that constant as an initialization for that array. So when we print these things out, we should see that basically, while we think of them as maybe in some sense being different things, our array and the name of the array in terms of our syntax is also just a pointer. This syntax where we use %p as our format string specifier in printf is saying, what is the address? Print me off the address of a pointer. It's just printing it as hex as we've seen, but that's one way to print our addresses. Name pointer points to wherever name pointer winds up being in memory. Again, as we noticed earlier, we oftentimes don't care exactly what that address is, but we know it's there somewhere in memory. It turns out in practice that if we initialize it as a constant like this, it does get put in yet a different region of memory than if it was just a variable that was either global or relative to a function. The pointer itself, if we go back to our definition, is our variable that stores the address or the location in memory of a variable of that type. So the pointer itself is also a variable, right? It is a variable that points to something. So we can also print out, if we were interested in knowing that, the address of the pointer itself, right? Let's go back to our mailbox analogy, right? the key had the label in it, and that was opening up the mailbox. Well, that key itself is also stored in a mailbox. The pointer itself is also stored in memory. So we can also print out the address of a pointer itself. Where is the pointer itself located? Technically, if we want to use the right phrasing here, when we do ampersand or and name pointer, that's taking the address of our pointer, not the value of our pointer. So that becomes a pointer to a pointer, right? That is the address of a variable that itself stores the address of some other variable. It is a pointer to a pointer. Now, what's unique now for this example is we can do the same exact thing for our array syntax as well. Name array is not set up explicitly as a pointer here, it's set up as an array. We can also print out the location, the pointer to name array, by just using what I keep calling the empty array syntax. Just the name of the array variable is a pointer to the first element in that array. If we don't, for whatever reason, want to use that exact syntax, we could also be more explicit for printing out what should be the same exact address on that next line. Here's a pointer. What I'm passing for that pointer is now the address of name array of 0. Name array of 0 being the first element in the array, address of that first element in the array. Otherwise, whether we have an array or whether we have a pointer, our functions that treat them as input operate exactly the same way. %s expects a string, expects an array of character variables. We pass it a pointer either way, whether it be the empty name of the array variable or just the pointer to what is an array of character values, and we get to print out that string. And we'll see in just a second, your scanf also works exactly the same way. We can then update our array variables or update our pointers and get a similar kind of result here. The actual, as we've talked about, the actual addresses don't matter all that much. Like, do I care that this is at 7 FFC versus some other particular value? But at the very least, you can see that when we have this constant initialization via a pointer, it does get put in a different region of memory than where our, what we've been referring to as stack variables get placed, our variables that are relative to each function. Name pointer is itself a variable that gets placed there in the stack. Name array also gets passed in the stack. And we can see that when we explicitly printed out the first element of name array, we get the same exact result. And that's the best I can show you that that is the case, right? The name of the array variable is the same exact value, returns the same exact address in memory as ampersand array of 0, because it is the first element in that array and where it winds up being located. This is a pretty long-winded way of answering, why have we been able to use scanf the way we've been using it all semester? I said it was okay from day one to just understand that this is how it works and just kind of use it and not have to really appreciate it much deeper. But all semester, we've been passing in these pointers to scanf. We haven't been calling it as such, but we've been passing it the addresses of these variables we want to update via scanf. Scanf takes our format string specifier, and based on how many of those it finds, it also takes an equivalent number of pointers as input. And it will update one by one, given a %d here, update the next integer it finds at the address that's specified. That is using that address or that ampersand syntax here. But what did I just mention? When we have an array of integers, the name of that array, just the empty array syntax, is a pointer to the first element in that array. So it's perfectly valid to do exactly that as well. Scanf %d and pass in an array as input. It is only going to update the first element in that array if you do that, and we'll be able to print that out and show that that's the case on that next line here as well. Similarly, for entering in characters, we can just use the ampersand operator, or we can just pass in a pointer to an array via the empty array syntax here. It should get the same exact result. And now we finally see why %s kind of works. Why, when we were doing %s to read in my first name, my last name, my string value, why we were not using the ampersand operator for that. Because we were defining an array, a character array in this case, and when we define that character array, when we want to provide that pointer to scanf or to printf, but it's certainly when providing it to scanf, We don't need the ampersand operator because the name of that character array is already a pointer to that first element in the array. Entering an int works as expected. Entering an int for which we provide the array syntax also works as expected. A works, B works, and hello, whatever, also works as expected for that program. So in some sense, this is nothing new. You've been doing this all semester. Hopefully now a little bit better appreciation for why that actually works. Why sometimes we've been doing that ampersand operator for scanf, and other times we've realized that we really don't need to. And you shouldn't, right? If instead we provided this here, that would be a syntax error. That shouldn't even work. I'm not entirely sure what that would even do, because syntactically it's still technically valid, but it's a pointer to a pointer now. It may wind up still working, but I don't think it would be guaranteed to. It still worked. It's technically incorrect. That syntax is the correct one. We provide the name of the array variable as our pointer. Skip through the rest of this that we already kind of talked about. We also briefly talked about pointer arithmetic, and I'll just bring it up again very briefly now. The nice aspect of this as a feature is that performing arithmetic on pointers actually works, I think, in the way one would hope it would work. It actually is aware of the size of the type that your pointer is pointing to when you want to then point to maybe the next object of that type. Let me just show you the example versus belaboring the point too much in terms of what's on the slide here. I would show you the example if I have it open. Let's open it up. Where again, we can set up our pointers explicitly by just setting that pointer variable to be the address of some other variable of that same type. When we do int pointer plus plus or versus car pointer plus plus or my custom structure pointer plus plus, the result is actually not equivalent to doing an integer arithmetic. It is similar in nature, but it is adding one pointer to that object. It is now saying I point to this object. When I add one to it, I want to point to the next object. Let's look as this boots here what that winds up meaning in practice. So again, we kind of just manually set up our pointers, print out the initial things that are being pointed to, increment those pointers, and then print out what the pointers were again. Where we left off last week was kind of playing around with what the compiler was doing in terms of optimization. I don't want to dive too deeply into that because it wasn't the point of this exercise. It was just kind of a side effect of the exercise. So I have my int pointer. I set it up to point to int2. I have my car pointer. I have it set up to point to car2 here. I print out both the values and the addresses corresponding to that. Then I increment those two pointers, and let's see how those values have changed, right? This is a big hex string. It's not that easy to see exactly how things have been changed here. But int pointer 1 up here, we can just look at the last few digits of it, ends in 108. That's in hex. Once I increment it, it doesn't go up by 1. It goes from, if you look at just the least significant digit there, it goes from 8 in the least significant digit to C, right? We do our hex, and we're not hex experts yet. You'll get plenty of time to be a hex expert later. 8, 9, 9, A, B, C. It goes up by 4, right? So C is 12, so it goes up by 4. The pointer is pointing to a location in memory, and at least in our C memory model, and generally what we have underneath the hood in our computer itself, the processor itself, we have byte addresses. So our ints are, in this system, 4 bytes long. When we want to point to the next integer, doing a plus plus operation is really saying, give me 4 bytes further along. Don't give me just 1 byte further along, give me 4 bytes further along. Now when I do the car pointer plus plus, and we can just quickly look at that value there, and I think you can see it ended in 6. When we did plus plus for that one, it ended in 7. So that one, in that instance, when we go to the next one, it added just 1, because each character is just 1 byte. So we're just going up by 1 when we do that plus plus for that instance. Again, we oftentimes aren't necessarily wanting to do so much explicit arithmetic with our raw pointer values here, but when we do have it and we do pointer plus plus, it is going to operate, I think, the way you would hope it would, which is it goes to the next one. It would be, so we can, plus plus is one way of doing it, but we could say like, equals int pointer plus one, right? The temptation is instead to say, oh, I know it's int pointer one plus one. The temptation is to say, oh, this is an int, so I actually want to do size of int and add 4 to it. But that would be wrong, because that's going to kind of double count those 4 bytes per thing. It would point to 4 integers later, and we only want it to point to 1 integer later. Now, why does it go from printing 4 to 3? We decided at the very end of Friday, as time was kind of rapidly running out, that at least tells us a little something in terms of when I write my program here. Again, we oftentimes don't care about the raw address of where things are placed, but this program gives us a hint as to what the compiler is doing here. That in fact, it places things in memory in reverse order. We originally are pointing to the value of 4, which is our int 2. When we say, give me the next integer, so go up in memory, it gives me the value of int 1, and it does the same for the car as well, right? It goes from E to D. So that just tells us, that gives us a hint that how things are getting laid out in memory for the variables we've defined. And that's true of the characters versus the integers in general, right? Which ones occurred first, which ones occurred last. In fact, the very first thing in memory is actually car 2, then car 1, then int 2, then int 1. They're actually showing up in reverse order in terms of where they are in memory. That's a pretty historic convention for how we lay things out with regards to our stacks. Where things got a little hairy is if we weren't being really explicit in printing out some of the pointers for int 1 and car 1. I think if we erased that line or commented out that line, what wound up happening? It went from printing 4 and 3 to 4 and then, for want of a better word, garbage and garbage here, which is a little counterintuitive, right? And this was as time was running out back on Friday. I didn't change anything with my logic in the code. I just got rid of a print. Why would getting rid of a print statement change the result of completely seemingly unrelated lines of code in my program? Again, if this were to happen to you, it would usually be a sign of some other bug you have. This won't happen just to mess you up while you're programming. If you encounter this type of scenario, it's a sign something else is probably not correct, for want of a better word there. Well, what is ultimately happening there? The compiler, as part of the very sort of basic set of optimizations it's going to perform, is going to look at the variables you've declared, int 1 equals 3, and it is going to determine as best it can, hey, you declared this variable, but did you really mean to? Do you actually need it or not? Did you have any point of having this in your program? And there's all sorts of complicated algorithms. There's whole courses on this particular subject and whole textbooks one can take on this subject. But for want of a better way to phrase it, it can determine, hey, if int 1 never leads to the result of anything that ever gets printed out, or updates a file, or somehow changes the state of your program in a meaningful way, the compiler's free to get rid of it. Same for car 1 in this example. So although the naming could have perhaps been a little bit better, we declared int 1 here. We never actually use it anywhere. Int 1 doesn't appear anywhere else in the program. The only time it showed up was on line 11, but I'd commented that out. Compiler is realizing then, you said you wanted int 1, but I know better. You didn't actually use it. It doesn't allocate memory for it at all. It gets rid of it. It just removes it entirely. So when it comes time to now increment my pointer and go to the next thing in memory, there isn't a next thing in memory. There isn't another value in memory there. And again, if I uncomment out that seemingly unrelated line to print out int 1 and car 1, we go back to having those values being located in memory. So we're continuing on pointers, but kind of moving from stuff that we already talked about last week to kind of moving on to a new topic here, which is my attempt to kind of motivate why we care about pointers in the context of dynamic memory allocation. Think in terms of the image processing we've done all semester, where again, we used a library that solved some of these problems for us, but assuming we didn't have that library, or we were working with a different library that left the responsibility to us as the programmer to worry about things like We have an image, we want to process that image. We want to convert it to grayscale, we want to apply some filter to it. We generally would not necessarily know the size of that image, how many pixels it is, the horizontal and vertical resolution, before we actually open it. So we always talk about, as part of our problem-solving process, that we have to think about our variables, what the sizes of those variables need to be if they are array variables, but sometimes it's not that easy to answer. I want to declare a two-dimensional array to store the individual pixels for my image, but what do I actually do if I don't know how big that's going to be? This is one way to phrase it. I want pixels of size n by n, but what if I don't know what n is going to be? Well, the temptation, I think, is to do something like this, right? Okay, well, let's read in n, and then when we declare our array variable, let's just declare it then of size n by n. That is referred to as variable length arrays, and it's something that's not actually universally supported in C, depending on which version of the standard your compiler is supporting and which compiler you're actually using it. In general, I think it's a correct statement to say, in the year 2023, for a modern system you will be using, for a reasonable set of values of n, that's a lot of caveats, but they're valid, this will not work. It'd be nice if it would. Other languages certainly let you do dynamic array allocation in such a way, and C in generally does not. So there's a couple caveats here. This idea that you can do a variable length array, you will find examples that work. You will find certain arrays and certain configurations that will work. For an arbitrary image of an arbitrary value of n is not going to work for you. In general, the assumption our compiler makes when I declare my array, int pixels of size n by n, is that that information is known statically to the compiler. That at the time it compiles your program and I hit that green run button in Replit, it needs to know what n is already. So that term we use is referred to as static memory allocation. It's done once, and we know exactly how many bytes that pixel array needs to be. We've been doing that all semester. We've been able to write all sorts of fun programs with static memory allocation, but it is a limitation that we have to know at the time we are writing our program. Using pound defines or other tricks gives us a little bit of flexibility, but in general, when we compile our program, we need to know what n is for our image. And that's pretty limiting, right? Because we want to write a program that's going to process all sorts of different images, and we want to be able to support that. We want to be able to support that properly. One possible workaround, and we've done this in a few different instances already this semester when sorting arrays and doing other stuff, is to say, well, I know I want to support different sized images, and perhaps I just put an upper limit as to what I can support. And say, well, my program's going to work for all sorts of images up to and including 1024 in the horizontal or vertical resolution. That's what I mean by max n here, saying, okay, I'm still going to do static allocation where the compiler knows how big my arrays need to be. And I'm just going to put an upper limit at as a compile time constant here. And it should work up until n gets larger than 1024, then it would not work in that case. That is valid. It's a workaround. It is quote unquote wasting memory. If you're processing a whole bunch of very small images, that is a proper waste of memory. You're maybe wasting megabytes and gigabytes over time here. But that's kind of the limit of what we can do with our current approach to allocating arrays. We either know what n is ahead of time, or we set a reasonable upper limit of what n can be, and we take a subset of that when it comes time to actually use some subset of that memory. Again, you can get pretty far with it. With the Lab 7 example, we knew by spec of that problem, there was exactly 108 notes we needed to allocate, and that was fine. And we allocated exactly that many. It wasn't going to become 109 notes tomorrow, so it was sufficient. But for that buffer of samples, right, where we also said, okay, we want exactly 2 seconds worth of sound in that buffer. Tomorrow, if I decided I actually needed 3 seconds, I have to recompile my program, right? I have to statically determine that it's actually, whatever that number would be, 44,100 samples times 3 seconds and not times 2 seconds. The alternative to that static memory allocation approach is referred to as dynamic memory allocation. In a dynamic memory allocation scheme, the amount of memory you have corresponding to a pointer that would correspond to an array is going to potentially change in time. It's going to grow and shrink over time. I tell at runtime, here's how many bytes I need for a particular array. And there's functions that provide you that chunk of memory corresponding to that. That allows you to determine, today on this execution, I need a 300 by 200 image. I allocate exactly that many pixels. Later, I need 1024 by 1024. I allocate exactly that much memory for that many pixels. It is the quote unquote proper way to handle dynamic memory types. And there's just certain things that you really can only do using dynamic memory allocation. That's the upside. The downside is it's just a little bit harder. And it's the kind of thing that if you do wrong because you're dealing with pointers and you're then referencing those pointers, you'll get segmentation faults. You'll get crashes when you do it and make a bug along the way. But it's just it's a necessary growing step for us as C programmers here. So primary function. Oh yeah, go ahead. Sure. Because in practice, we will be processing data of an arbitrary and dynamic size. That we'll be processing just images, for example, and the size of the images is not something that we know is going to be fixed a priori. It's going to be something that will change dynamically over time. And so we want our memory usage to kind of grow and shrink over time to handle data itself, which is potentially dynamic. Again, we've avoided that this semester by kind of just working around the fact and setting things like max n in our program. Well, that's also a limitation, right? Max n may need to change over time. We want to be able to say, this program today does 1024 by 1024. Tomorrow it does 2048 by 2048. And this is one approach, and this is kind of the standard approach to support that. The first function you get to become familiar with is referred to as malloc. Stands for dynamic memory allocation. And in some sense, this is all it is. You start off with a pointer, right? Syntactically, if we recall, our pointers are type dependent in C. There is no pointer type. We say, I have a variable data type, and I have a pointer to that type of variable. So that could be int, if you don't want to think of it as an abstract, undefined data type. That's our int star. That's our pointer. And now, as opposed to using the ampersand operator to set it to an address of something else that's already been allocated, we're going to call this malloc function. And we are explicitly saying, as I call this malloc function, that was in the wrong order, the input and the only input to that function is the number of bytes that we want. Give me 74 bytes of memory. Give me 6 bytes of memory. Malloc returns a pointer that doesn't have a type associated with it as a void star return. So best practice is then to explicitly cast the return of malloc to match the pointer type that you already have. It'll just be a warning if you don't have it, but that is best practice here. So that's a little abstract, but this is in practice all it winds up being here. So if, for perchance, we wanted to allocate 15 integers in what would ultimately be accessed as an array called A, this would be one way we could then do it. As opposed to saying int A of 15, again, this makes sense if 15 is something we don't know until we're running the program, not at the time we are writing the program. But if we wanted to allocate those 15 integers, we start up by setting up a pointer. That's our int star A. And then we call malloc. We cast it to int star. So type that part first. Hey, what kind of pointer am I allocating? It's an int pointer. Put the cast there up front. Call malloc and specify the number of bytes that we actually want here. But that particular usage example here makes a certain assumption. What assumption does that example make? That may or may not be a true assumption. That's right. That's exactly right. That makes the assumption that each of our integers is 4 bytes. We didn't belabor the point earlier in the semester, but it turns out the way the C specification is written, our integers are generally 4 bytes, but they can actually be more depending on the system. And here you've written a piece of code that works on your computer today, and you download it next week on a different computer, and all of a sudden it's not what you expected because we allocated 60 bytes, and maybe that was actually not enough for our purposes. So the quote-unquote correct way then to use malloc, and the muscle memory I want you to develop when doing dynamic memory allocation, is to instead use that built-in size of operator every time we are using malloc to specify how many bytes each individual element we're interested in are going to require. Again, if it wasn't something as simple as an int or a float, you would need to do this anyway, unless you want to count up exactly how big your structure is on a byte by byte basis. So we would have to do it anyway, but in this case, this is the kind of general syntax I'd want you to do. I want you to be able to look at this and say, inside of malloc is 15 times size of int. Yeah, that's 60 bytes, but we don't really care even about that. 15 integers is what we've allocated. Because however many bytes we need for an int, that's what size of int returns. And so I want 15 times that. That'll give me 15 integers here. Yes, it'll give me the same on our replit system we're running on. This will work on any system. Yep. Mm-hmm. I'm not sure I understand your question. So it said we wanted to do 16. Yep. Well, I mean, certainly it's not the end of the world, right? I mean, the trade-off is you've allocated one more integer than you maybe potentially need. It's an interesting perspective, right? It's an interesting thought, right? If you allocate too much memory, your program probably still works, right? You allocated 16 and you only needed 15, your program's probably okay, right? If you allocated 15 but you actually needed 16, your program's not going to work, right? That's going to crash when it tries, or give you an incorrect result when it tries to access A of 15, the 15th offset from 0. So that my advice is not officially to allocate more memory than you need. Generally, though, think about what you're trying to do. Yes, technically, if it's always 15, you could just hard code that in your program and do static memory allocation. The more general case is this value will be n or some other variable, and you have to think about what n needs to be in y, or is it n squared, or is it n plus 3, whatever it needs to be. You have to think about that first, and then you usually don't run into that issue of allocating too much memory because you've thought about, I need an array, a dynamically allocated array. How big does it need to be? Once you know that, then you just plug that equation into your malloc function, and you get the result that you expect back out. Let's visualize what's happening in memory one more time. Again, as a programmer, I think this will help you become better at debugging when things go wrong, but you can oftentimes get pretty far without having to visualize this as well. There's fundamental differences between doing our static and our dynamic memory allocation. We've been doing static all semester, and we've been talking about the scope of our variables, right? What is the lifetime for which referencing a variable is valid in our program? Scope then also directly corresponds to how long that memory is allocated for that variable in our program. They're actually exactly the same thing in this context. I have a function. Inside that function, I declare a variable. That variable scope is only valid inside that function, and it actually only exists in memory. That location in memory is only valid while I'm inside that function. So it's kind of a side effect that we have started everything in main, and we're always staying in main, that something declared in main will live for the life of your program. But in general, when we write a function, our variable only is going to last if it's allocated statically, as long as we're within our residing function. Dynamic memory does not work that way. Other programming languages spend a lot of intellectual effort and implementation effort in doing what's referred to as garbage collection, which is freeing back up the memory that you allocated but forgot about, that you don't actually need anymore. There's implications for performance there. It makes your life easier as a programmer, but your programs may not be as efficient ultimately. C does not have that capacity to do garbage collection. Someone could potentially be very clever and try to implement it, but by default, at least, there's no concept of garbage collection. You are the garbage collector when you write your C programs. Another way to phrase that is, when you malloc memory in C, it is your responsibility as the programmer to free up that region in memory. And that itself does pose a challenge. It may not look like it. You may look at this and say, okay, I allocated 15 integers. I need to make sure, there's a function call, I need to make sure I free it later on. That's true. In practice, though, you have lots of different things allocating lots of different memory. All modern programming is involving allocating dynamic memory. There's all sorts of cool things we can do only with dynamic memory allocation. Keeping track of who allocated what how long does it need that memory, and when that memory should then be free is one of the challenges of working with pointers, is one of the challenges of doing dynamic versus static memory allocation. So that's the other major difference about our stack, where our variables are put when they're declared relative to a function, and the so-called heap, where our memory is put when we are doing this dynamic memory allocation here. We can visualize it. We already did this once previously this semester, but let's do it again. As we statically allocate memory relative to each function, the thing the compiler can take advantage of is the fact that as we call our functions, they will return in the order in which they're called. A calls B, calls C, C will return, then B will return. That is a last or first in, last out type of operation here. First function is going to be the last one to be completed. Main will be the last function to be completed. We can make use of a comparable data structure, first in, last out queue, otherwise referred to as a stack, to keep track of the memory for each corresponding function. So if we have in this code main that calls foo, that calls bar, we would have something of a function call graph that looks like that, right? Main calls foo, calls bar. As they return, the arrows kind of go back in the opposite direction. Bar returns to foo, returns to main. Our memory allocation follows a very similar pattern, where in main, we have the so-called stack frame for main. We have the region of memory dedicated to main's variables, plus some other runtime information. Main then calls foo. In doing so, we statically allocate the amount of variables declared inside function foo there. That is foo's stack frame. And then foo, as it calls bar, we get bar's stack frame. When bar returns, we return that memory back to the system. When foo returns, we return that memory back to the system. And ultimately, when main returns, we return that memory back to the system as well. That is in contrast to what happens when we do dynamic memory allocation. Because there's no guaranteeing of any sort of order between allocation and freeing, or allocation and deallocation, we can't make use of as simple of a data structure to keep track of our memory. It can happen in any order, and for that reason, memory can in fact get quite fragmented, that you have partial things here and partial things there. So there's a special type of data structure, and the name of it is sufficient to know for now, called the heap, that is set up by most systems implementation of that malloc to keep track of where things are going to be placed next in memory. So this example here is using 3 separate calls to malloc. So we allocate A. It's going to get placed somewhere else in memory, separate from the stack. We're then going to allocate B, followed by C. And then there's a call to the function free. And we haven't talked about it. We can kind of guess at what it's doing. Free takes as input a pointer to something previously allocated via malloc, and it returns that memory. It says, I don't need B anymore. I'm done with B. B is no longer valid. It's going to essentially remove that region of memory corresponding to B. Now, what makes this different again from our stack is the relative ordering. There's no guarantee we do A, B, C, then C, B, A. In this case, we did A, B, C. We removed B. Now perhaps we do D, E, F. Those are going to go wherever they need to go, wherever space is available in memory. D could go here. E could go here. Perhaps there's not enough space for F, but if there is, it goes right there as well. For that reason, every time we use these pointers, we should in fact, with dynamic memory allocation, we should in fact be checking, is my pointer actually valid first? So syntactically, the quote-unquote correct way to do that is to call our malloc function, and when we're here on Friday, we'll do this more explicitly, to call our malloc function and to check, did the pointer we get back, is it valid, or is it a so-called null pointer? And if it is, well, we oftentimes can't recover from that because something very bad happened in our system, we ran out of memory, or accessing something that's already been freed, but at least we can detect that that happens without properly crashing. We can return an error to the user saying, this pointer is not valid and something is wrong with your application's execution. So in terms of awareness of our memory, I think this is kind of sufficient. We have these 2 different blobs of memory now happening in parallel. We have this stack. Again, if you think of the stack, let's go back here. The stack is this. Function by function by function, whatever we've declared inside that function gets placed on the stack. We'll talk about recursive functions later on this semester, where it's function, function, function all the way down because it's calling itself. And the way that works is by having a stack that even if it's foo calling foo, that still works out because it's going to be different regions on the stack corresponding to each call of that function. So we place things on top of each other like a stack of plates is the old analogy people would use. Whereas heap is kind of more anything goes. Give me the next available region of memory to place what I need to allocate. If I free it, then that opens up more memory region for somebody else to later be allocated. We have both these things and they operate on totally different principles. And so sometimes immediately obvious question is how do we prevent things that get dynamically allocated from colliding with things that get statically allocated? And the technical answer is we technically don't, which is kind of a crazy thing to think about, that we have all this code, billions and billions of lines of code running all sorts of the world's most critical systems. And the only mechanism we have to check whether we've run out of memory is to kind of check the result of calling malloc and to determine did we get something valid or not. By convention, the way we try to minimize this happening is by just kind of splitting up the memory in half. So assuming the stack and the heap want to stay away from each other as much as possible, by convention, we put dynamically allocated things on the heap and statically allocated things on the stack. And as the heap grows dynamically over time, and as the stack as well grows dynamically over time, they actually wind up growing towards each other. So the convention is the stack grows backwards in memory from high addresses down to low addresses. And by convention, the heap grows upwards in memory from low addresses to high addresses. What prevents them from colliding? Actually, nothing. Eventually, you allocate enough things on your stack or on your heap, your system will crash, your program at least will crash. But that convention kind of minimizes the likelihood that that would happen because you have the whole memory space to split up. As a final point with regards to that, if we go back to our, was that array, what was it called? This array pointer arithmetic here, why was int1 at a higher location in memory than int2? Because of this exact picture. Now this is just a single stack frame, but even then within that stack frame, our memory is growing backwards in address spaces from very high address spaces to relatively low address spaces. If later I decide I want int, and this will break the program pretty good here, if I want int pointer 1 to instead be a dynamically allocated region of memory, let's do 255 integers. And that needs to go in a different library if we don't want a little compiler warning there, standard lib.h. If instead I want it to be to some dynamic region of memory, that resulting pointer, when I print it on down later on down here, it's going to return nothing of valid, but that location is in a much lower location in memory. The pointer can go wherever we want it to. Here it was pointing to something that was on the stack. Down here it's now pointing to something that's on the heap, and the location has changed significantly from where it was as it got placed, pointing to something here, to getting placed to something down here. Don't leave yet. There's still more fun to be had. Let's all open up Canvas and take this week's quiz.